You know, we've all seen them, those massive power plants and the endless spider web of high voltage lines crisscrossing the country. But what you don't see is the invisible defense system, this hidden network of sentinels that keeps it all from falling apart. Today, we're going to pull back the curtain on the incredible world of protective relaying. So here's the game plan. We'll kick things off by looking at the grid's nervous system. Then we'll see what happens when lightning strikes, when things go wrong. We'll dig into how these protectors actually sense danger, the layers of defense they use, and finally, we'll get to the really cool part, why their incredible speed is the key to a powerful and reliable grid. All right, to really wrap our heads around how our power system protects itself, we need a good analogy. So let's stop thinking of the grid as just a bunch of wires and machines and start thinking of it like a living thing. And this living thing has an invisible nervous system. It's constantly feeling, it's sensing, and it's reacting in just fractions of a second to stop a disaster before it even starts. Honestly, without it, the grid as we know it, well, it just couldn't exist. It's that important. I mean, the sheer scale of this thing is mind-boggling. It's this huge, sprawling network that's basically the lifeblood of our entire modern world. But here's the kicker. For all its power, it's actually super fragile. A single failure, if you don't catch it, can set off a chain reaction that is just catastrophic. So what is it protecting us from exactly? Well, in the biz, failures are called faults. This could be anything, a tree branch falling on a line, a piece of equipment failing, or, a massive lightning strike. Let's take a look at the anatomy of one of these events. At its core, a fault is basically a short circuit. It creates this path for electricity that it was never supposed to take, a path with almost zero resistance. And basic physics tells us that when resistance drops through the floor, the current goes through the roof. We're talking a colossal, instantaneous surge of pure destructive energy. And the consequences of that surge, they are severe. I mean, we're talking about millions of dollars of equipment just vaporized in the blink of an eye. Even worse, one fault can create this domino effect, tripping other parts of the system and leading to these cascading blackouts that can plunge millions of people into darkness. The stakes are incredibly high. So, how does the grid fight back against that kind of chaos? It does it with reflexes, incredibly fast, totally automated reflexes. And this is where our hero, the protective relay, finally enters the story. Protective relaying is the grid's nervous system. These relays are the smart devices. They're like the nerve endings spread all throughout the network. And they're not just sitting around waiting for something to break. They are constantly, 24/7, monitoring the vital signs of the grid, the voltage, the current, the frequency, looking for any tiny sign of trouble. When you boil it down, the relay's job is actually pretty simple. It's a three-step process. First, it senses something abnormal, like that huge surge of current we just talked about. Second, it decides if that surge looks like a dangerous fault. And third, if the answer is yes, it acts. It sends a command to a circuit breaker telling it to open up and cut the power. Sense, decide, act, all happening in an instant. Now, this is the really clever part. This is how the system avoids a total meltdown. The whole grid is broken up into these zones of protection, and each zone is watched over by its own set of relays. So when a fault happens in one zone, the relays act to cut off only that one broken part, letting the rest of the grid run like nothing even happened. It's like performing microsurgery instead of a full amputation. But what if that first line of defense fails? What if the relay doesn't work? Well, any really good system has redundancy, right? Protective relaying is built on this idea of a layered defense, making sure that no single failure can bring the whole thing crashing down. Think of it like this. Primary relaying is your team of first responders. They're on the scene, they're fast, they're precise, and their whole job is to contain the problem right there, in its specific zone immediately. But if for some reason they can't do their job, that's when the backup relaying kicks in. This is your safety net. It waits just a moment, giving the primary system a chance to work. If it doesn't, the backup system swings into action, disconnecting a much larger section of the grid just to be absolutely sure the fault is stopped. It's a bit of a blunt instrument, but it guarantees the problem doesn't spread. There's this great line from one of the classic textbooks on this subject that just nails the philosophy here. While having a backup system is absolutely critical, you really, really don't ever want to have to use it. It's the proactive, careful maintenance of those primary relays that keeps the grid healthy and reliable day in and day out. So we've got these brilliant devices, we've got layers of defense. But for this whole system to work, there's one ingredient that is more important than anything else: speed. And this is where we get to the ultimate payoff of this entire system. Get this, 1/60th of a second. In the US, that's just a single cycle of alternating current. It is literally faster than you can blink your eye. That is the timescale that these high-speed relays are working on. And that incredible speed is what stops a fault's destructive energy from spreading and causing a system-wide collapse. But here's the wild part. Speed isn't just about preventing damage, it's about increasing power. See, the faster the relays can clear a fault, the more stable the whole grid becomes. And a more stable grid can be run closer to its physical limits, which means we can push more power through the exact same power lines. Making the relays faster is one of the cheapest ways to boost our grid's capacity, potentially saving billions of dollars on building new infrastructure. So let's bring it all home. Why does this invisible system matter to you? Well, it's what keeps your lights on by stopping those massive blackouts. It maintains the stability that our entire economy is built on. And by safely squeezing more power out of the lines we already have, it provides this huge hidden economic benefit to all of us. You know, in a way, the protective relay was the original smart grid technology. It's been learning and getting better for over a century. But as we add all these new, complex things to the mix, like solar, wind, and millions of electric vehicles, the grid's nervous system is going to face a whole new set of challenges. So the real question for the future is, what new, even faster reflexes will it need to learn to keep our power flowing?